Hi, I'm Scott Knockleby. In this video, we're going to look at some examples of assigning modified D&H parameters. So, by the end of this video, you should be able to assign modified D&H parameters to different robot manipulators. The first example we're going to look at is the planar 3R manipulator that we've looked at in other examples. Okay, so it is a revolute, parallel, revolute manipulator because it's in the plane. That means Z1, Z2, and Z3, the joint axes, are all coming out of the page, and they're all parallel to each other. Now, first step in solving these problems is to draw a zero displacement diagram. And remember, a zero displacement diagram means what does the robot look like if all the joint values are 0. Now, this shouldn't be confused with what sometimes referred to as the home configuration of a robot. The home configuration can be any joint angles you set. But in zero displacement, it's when our values are all 0, and it's how we assign our D&H parameters. So for this robot, we're going to start with Z0 coming out of the page. That's our base frame. And we're going to have X0 going to the right. And we'll just draw it in, but normally we'll just omit the y-axis because we don't necessarily need it in order to define our D&H parameters. So by convention, we try and assign our Z1 to be coincident with Z0. So we're going to make Z1 coincident with Z0. And in zero displacement, that means that X1 would be in this direction. Obviously, if theta 1 has a value, there will be an angle between x0 and x1, but when theta 1 is equal to 0, x0 and x1 line up. All right, we now have a distance or a length of L1 before we get to Z2. Z2 is parallel to Z1, so it's going to be coming out of the page. So this is Z2. And again, in zero displacement, we will have x2 collinear with x0 and x1. Again, once theta 2 has a value, there will be an angle between x1 and x2. And we can keep going. So we'll have L2 now. That brings us to Z3. X3 will be here. And then we have L3. That brings us to our end effector, or we often will call that our tool frame. So we're going to call it Z tool. And we'll have X tool here. Okay, so we have our zero displacement diagram. And once we have that, we can start filling out our D&H table. Okay, so here's our D&H table. This is frame I minus 1, so we're going to start at frame 0, and we're going to go to frame I. So frame 1, and then we're going to go from 1 to 2, 2 to 3, and then 3 to tool. We have our 4 modified D&H parameters, alpha I minus 1, sorry, AI minus 1, alpha I minus 1, DI, and theta I. All right, so let's start filling the table, and we're going to go row by row, starting at frame 0 to frame 1, and then so on. So at frame 0, all right, to get to from frame 0 to frame 1, all right, remember that AI minus 1, okay, it's the distance between Zi minus 1 and Zi measured along Xi minus 1. Well, they're coincident, so there is no distance between those two. Okay, so we're going to have 0 there. Okay. Alpha I minus 1 is the angle between Zi minus 1 and Zi. All right. Well, again, they're collinear. So our angle is going to be 0. All right. DI is the distance from xi minus 1 to xi measured along Zi. It's also 0 for this case. And then our last theta I, well, that's going to be our joint value. And although it's 0 in this drawing, we're going to keep it as a variable. So we're going to say this is theta 1. All right. Now we're going to go from frame 1 to frame 2. All right, and so AI minus 1 is the distance between z's measured along x. So that distance in this case is going to be L1. The angle between z axes, well, they're parallel, so that's 0. There's no distance between x's, so that's 0. And then we're going to have theta 2. And we'll have the similar for 2 to 3. We're going to have L2, 0, 0, theta 3. And then lastly, we're going to have L3, 0, 0. And now there's no angle associated with the tool. All right, it's not a joint, so this is going to be 0. And that is our completed D&H table for that robot. So one suggestion to practice these is to just start with the 0 displacement and see if you can fill out the table on your own without looking at the video. Another technique you can try is you can actually start with the D&H table and see if you can draw the 0 displacement diagram. All right, so with this D&H parameters, you should be able to draw your 0 displacement diagram. Let's look at another example here. All right, and so this is a spatial manipulator. So this means it's not operating in the plane, it's operating in 3D space. It's only 3 joints though. All right, so it's just a positioning device. There's no, because we are only controlling three degrees of freedom. For full spatial motion, we need 6 joints. But we can think of this as the main arm, the first 3 joints of a robot. So this robot is a spatial revolute joint. So there's a revolute joint, so joint 1. It's perpendicular to a prismatic joint. So let's make a note that this is P means prismatic. Okay. And then, so that prismatic joint translates in and out here. And then we have a final revolute joint, which is parallel. It's actually collinear with Z2. All right, so joint 3 rotates. So again, a first step before we can fill out our D&H table is to draw the 0 displacement diagram. All right, so we're going to choose Z0 to come be up. All right, and we're going to have X0 go into the page. I could add Z0 coming out of the page or going to the left, and you have freedom to draw how you want to choose which direction Z0 is in. Your drawing would just be rotated from what I'm drawing. Okay, so we have Z0 and X0. And like before, we always want to try and assign Z1 to be collinear with Z0. So we'll have Z1 here. And in 0 displacement, we're going to have X1 here. And again, once there's a value theta 1, there's going to be an angle between X0 and X1, but in 0 displacement, there isn't. All right. We next have, we're at joint 1 and we want to get to joint 2. We know joint 2 is perpendicular to joint 1. All right, and so that means our Z has to be perpendicular to Z1. Now we could draw it in this direction, but because X is already in that direction, it's better to draw Z2 this way. All right, and so we're going to have Z2 here. That's our prismatic joint axis. And we're going to have some length D2 associated with that. All right, so that's going to be the D2 is the joint displacement of our prismatic joint. Now, in zero displacement, we could draw D2 as 0, but then it would get kind of hard. So we're going to actually give D2 a bit of a value here just so we can show how the axes are. All right, and so that distance D2 brings us to our X2 axis. All right. We're at frame 2 now. We want to get to joint frame 3. All right, we know Z2 and Z3 are collinear, so we know this is going to be Z3. Okay. There's going to be a length L3, and we can draw that on our drawing here. All right, we're going to have a D2 length, and then we're going to have an L3 length. Okay, and that will bring us to X3 here. And now we're going to say that our tool frame is the same as frame 3. So this will be X tool, and this will be Z tool. All right. With that done, we can start assigning our D and H parameters, and just like we did in the previous example. So our first value is AI minus 1. All right, going from frame 0 to frame 1. All right, so remember, A is the distance between Z's measured along X. Well, Z0 and Z1 are collinear, so this is 0. Alpha is the angle between Z's. Again, they're collinear, so this is 0. D is the distance between X's. That's also going to be 0. And then we have theta 1, our first joint angle. All right, we're at frame 1 and we want to go to frame 2 now. Okay, so A is the distance between Z's. Well, Z1 is up and Z2 intersects Z1, so there is no distance, so that has to be 0. All right, now we get to alpha. Alpha is the angle between Z's. Right, so Z1 is up and Z2 is in horizontal. So obviously there's going to be an angle between the two. And in this case it's 90 degrees. All right, now we need to determine the direction of it. So to do that, you stick your thumb along the positive X1 axis. All right, this finger up is your Z1 and we're rotating. So we're curling our fingers around our thumb to get to Z2. So we know that's a positive 90-degree rotation. All right, and we're actually going to write it in terms of radians. So that's going to be pi over 2. All right, our D value is the distance between X's. So there is a distance between X1 and X2, and that value is D2. All right, and D2 is our joint variable for this second joint. All right, D2 is what's changing. Okay. Now for theta 2 is fixed. And theta 2 is the angle between X's. Well, in this case, the angle is fixed, it's 0. Okay, so there's no theta 2 variable. So you'll either have, for revolute joints, you'll keep this as a variable, and for prismatic joints, you'll keep the D as the variable. All right, so now we're at frame 2, and we want to get to frame 3. Okay, there is no distance between Z's, so this is going to be 0. The Z2 and Z3 are collinear, so alpha is going to be 0. There is a distance between X's, so that's going to be L3. And then we have our theta 3 joint value. All right, and lastly, just to complete the table, well, frame 3 and the tool frame are equivalent, so this means our parameters in our D and H table will all be 0. All right, and so that completes the D and H parameters for this 3-joint spatial manipulator.